Hello, I'm Paul Dix, and today I'm going to talk about the journey of InfluxDB, how we've developed it over the last 9 years. Now, when we think about InfluxDB, we think about it in these kind of three different phases that you see here. The first is when we first created it back in 2013 up until 2019. That was basically the pre-1.0, 1.0 up to 1.8 phase. Then from 2019 to 2022, where InfluxDB was very much defined by our efforts in 2.0 and with the language Flux. And now we're moving into a new phase, 2022 and beyond, with InfluxDB IOX, which is the new core of the open source time series database. So in this talk, I'm really going to be focusing on this beginning phase of 2013 to 2019 and the IOX phase. And through that, I'm going to have a couple of talk themes that we'll be exploring. So the first I'd like to talk about is, what are time series even? And then use that to inform, what does that mean about what a time series database is? So first, what is a time series? So this is the definition from Wikipedia. It's a series of values of a quantity obtained at successive times, often with equal intervals in between them. And Wikipedia even gave some examples. So the first would be measurements of tide levels in the ocean. So here we have tide levels for Brooklyn, where I am, by the hour. It could be sunspot activity measured, on a regular basis, as in this chart. Or it could be the closing values of a stock market index like the NASDAQ over successive periods of time. Hopefully this one isn't giving you too much heartburn. But ultimately, the way we think about time series at Influx is that they're really just a method for interpreting and understanding data. They're a way to summarize data and compare things over time, ideally so that you can learn something from it, gain some insight, or build automation around that system and alerting around that system. So here's a single time series viewed another way, just as the actual data itself in a time series, right? So we have an array here, and we have pairs of value time pairs in ascending order, where the values are float values, and the times I have here are just variables, T1, T2, T3, T4. Now, in a time series, these times could be equally spaced apart, right? Once a second, once a minute, once a day, or they could just be the times that something was measured or something occurred. Now, how does this play into databases? So I think there are two ways to think about time series databases, right? There's one type of time series, which is you store the values of the time series directly and you store the metadata around it. That's what I call like a more pure play time series database. And then the other way to view a time series database is actually that it's not a time series database at all. It's just a system that allows you to compute time series on the fly from raw underlying data, whether that's, individual events and records in a relational database, or it could be data in an object store, or whatever it is you're looking at. Now, let's come back to our story with InfluxDB. First, I want to set a little bit of context for how things looked in the open source world back in 2013 when we first started working on it. So back then, one of the systems that people know really well and have been using for a while was RRD tool. So it was first released in 1999, and it was basically a tool and a file format for storing time series data and creating graphs like you see here on the right. RRD actually stands for round robin database. So basically, it's a file format structure for what's called a round robin database. So in a round robin database, you have a fixed number of elements. Here in our example on the slide, we have 20 little boxes. Those are the different elements. In each of those elements is a value, right? It could be like a float 64. It could be an int 64. And then what you have is a delta of time between each of those boxes. So here, what I've said is we have 60 seconds. So when you move from one box to another, 60 seconds of time has elapsed. What you'll need then to know the time that any of those values occurred is the starting epoch and the actual marker for where the starting epoch is, right? So here we have the arrows, you have T0, T1, T2, and then T20. So T0 is essentially where the start epoch is. T1 is start epoch plus 60 seconds. T2 is start epoch plus 120 seconds, and on and so on and so forth until you reach T20. So how this works when you actually write data into the database is you write the value into the spot you want, right? And you move the T0 marker and you move the start epoch, right? So essentially, with each passing minute, you take a new measurement and you write it into the database and you just keep filling this in, right? So it's a fixed size in terms of the size of the database itself. And again, this is just for a single time series. So the next one we'll look at from back in this time is a system called Graphite. So Graphite was originally developed at Orbitz and was first released as open source in 2008. It had a UI and added a different data model around time series that was hierarchical. This gave users a way to organize their time series or metrics, as Graphite referred to them. So this was the UI that Graphite had. And we have a graph on the right, and we have a way of organizing the metrics on the left. And if you look deeper at the metrics, there's a tree structure here. So that is the hierarchical data model. And in Graphite metric names, those different spots on the tree would be separated by periods, right? So you'd have graphite, period, carbon, period, like whatever. So that organizational structure was actually an artifact of the underlying implementation, right? Because what it was a file system with a bunch of different directories, and at the leaf of the directory would be the individual time series file, which was just a round-robin database. So inherent in the structure of both RRD and Graphite is this idea that time series are all regular, right? Time series are all samples taken at fixed intervals, right? And that's kind of limiting when you think about it. But people developed tooling to help them actually work with these systems. One very popular tool was called StatsD that was originally invented at Etsy. So what StatsD was, is a text-based protocol for conveying metrics over UDP and a server implementation that gathers events and metrics and aggregates them and sends them to Graphite. Now, in my slide here, what I actually have is applications transmitting the StatsD protocol over UDP to a Telegraph agent, right? Telegraph is the data collector that we created to write data into InfluxDB. And what Telegraph is doing is it's aggregating those metrics and then writing them into InfluxDB here. But in the traditional setting, you'd have StatsD writing into Graphite. So the next and last time series database I want to explore before we get to the start of InfluxDB is a project called OpenTSDB. So it was originally developed at StumbleUpon and released in 2010. And it's the first time series database that I was aware of that added this idea of tags as a way to organize time series data and a way to organize metrics. The other thing is the underlying implementation wasn't reliant on a round-robin database structure. Basically, it was Java Web Services layered on top of HBase as the data store. So HBase is the database in the Hadoop ecosystem, very similar to things like Cassandra or Bigtable or DynamoDB. So here's an example of some OpenTSDB data. So on the left, you have a metric name, which is just a string. Then you have the epoch, right? That's the timestamp. You have a value, which is either an integer or a float. You have the sets, and then you have the sets of tags, right? So tags are key value pairs where the values are strings. So the idea was you'd use those tags to organize this time series data. Now, one thing about the implementation of OpenTSDB is that because of the way everything was built, they actually had a recommendation that you limit the number of tags to no more than 6 or 7. They said otherwise the cost of storing new data would be dominated by the tags themselves, which would be constantly writing in more data. So that was a limitation that existed at that time that people were frequently running up against. So all three of those examples are what I call examples of time series databases that store time series, right? They store the actual time series data, and then they store metadata, which allows you to kind of like organize and explore and slice and dice the time series data in different ways. So this is the context into which we created InfluxDB in 2013. And here's the main section of the first website that we put up, right? This is before we even had a logo. And what I wanted to point out about this website actually is that at that time, even in 2013, we were talking about time series, metrics, and events, right? So in my mind, time series and metrics and events are actually contained within time series, right? Time series is a superset of those things. But basically, metrics are those regular sampled time series, right? The kind that previous three databases I showed do. Events are something completely different, right? Those are raw events from which you might be able to compute time series on the fly. The other interesting thing about this is the scale that we list here, right? We say track 100 metrics or 1 million. And of course, now when people talk about metrics use cases, frequently when they're talking about very large scales, they're talking about as many as 1 billion individual time series that they're tracking. But really the point I wanted to make here is that even from the very first days of InfluxDB, our vision was always that InfluxDB would be a useful tool for both metrics and event data. Over the course of InfluxDB's lifetime, we've had a couple of different data models. So this is the data model that we introduced at the very beginning of InfluxDB and the one we had all the way up to 0.8, which was released in November of 2014. What you can see here is that we had this concept of a measurement, which is basically like a table. And then we had a bunch of different columns, and every single table would always have a time column. So you have individual measurements that you're writing data in. We also introduced the first version of InfluxQL at this point. And InfluxQL looks largely the same today as it did back then in 2013, just with some additional features. So here's an example of a query from that early system, right? We're getting the value from response times for the last hour and just the first 1,000 values, right? The underlying structure of InfluxDB at this time was it used LevelDB as the storage engine. So LevelDB was an open source project, originally built at Google, and it was super efficient for ingesting a bunch of data really, really quickly. And the way we organized the data within LevelDB made a query like this very, very fast, right? We could index into a specific measurement and column at a specific time and give those 1,000 values, right? So this was something that even that early version of InfluxDB was very good at. However, if you add filtering, like we do on this query here, where we're now looking at not just the last hour of data from the value column, but we're also filtering it by something that's in the server column. What that means is we have to actually do a range scan over that period of time to find the values that hit that criteria. So essentially what this meant was as tables of data got larger and larger, they had more volume, they had higher velocity, the query performance that you got would slow down, right? It kind of resulted in a poor user experience for people who had that kind of schema. So what users ended up doing was they would break out their data into many, many different measurements. And we saw some users have, hundreds of thousands of measurements where they actually encoded metadata into the measurement name to get things to be fast. And at this time, the most common things we saw were people would encode a graphite metric name as basically just the measurement and then use that. So it kind of created a suboptimal schema design for the system. So in November of 2014, we released the last of these early prototype versions of InfluxDB. Right, this was 0.8. And at this point, we knew we'd have to make some sort of change to give people the user experience we wanted, right? We wanted something that would be super easy to get started with, as InfluxDB was, right? You could just write JSON blobs. It would create the schema and the structure for you on the fly. You wouldn't have to define that up front. But we needed something where the schema design would kind of direct people in a way where the underlying indexing structures of the database would give them fast query results. So what we did at that time was we decided, you know what, let's switch to this tags-based model, right? So we added tags and line protocol. Line protocol was a different way to represent the data to write it in as quickly as possible. So here we have an example. Obviously, we have the measurement name. We have tags, which are key value pairs, where the values are strings. That's the metadata around the time series. Then we have fields, which are key value pairs, where the values can be integers, floats, booleans, or strings. And then finally, we have a timestamp. And the reason why we created line protocol at this time was basically as a performance optimization, because the Go parser in JSON wasn't that fast at the time. And we found we could actually parse line protocol 24 times faster than we could JSON. So that was one benefit. The other benefit that we found over time was that line protocol was actually very readable. It was easier for people to use to debug, and they could see the data and what was going on. So let's dig into the underlying implementation that we created to support this user interface of tags and line protocol. So the first is what's called TSM. So we created our own storage engine called the Time Structured Merge Tree. And it was inspired by the log structured merge tree that was actually what Level DB was. But instead, we wanted to make time a first-class citizen, and instead of storing individual values, we wanted to store blocks of time series, where the time series is a time value pair, right? So in this example, we have a TSM file or a set of TSM data, and here at the beginning, you have a pointer to series number 1, and then you have time ascending blocks of data for that time series. And then you have series 2, time ascending blocks of data for that time series, and so on and so forth. So that's actually just the raw time series data. The other thing we needed to create was a way to organize the metadata, the measurement name, the tags, the fields. We needed a way to map all of that to the underlying time series so it could all be looked up. So what we did was we created an inverted index around that. So here on this slide, we have some line protocol at the top. We have 3 separate lines. And basically, if we want to translate that, we can translate that into the underlying series that get created below, right? So weather is the measurement. We have a city, we have a state, we have a zip code, we have temperature and humidity that we're measuring across all of these. And then we can see that this actually creates, these 3 lines actually create 6 individual time series, one for each city, state, and zip for temp, and one for humidity. As we can see, those time series map into like a specific ID that we give them, right? Series 1 through 6. What we do is we put those into a posting list in the inverted index. So the first thing we need is the set of measurements. So in our case, we have weather, and we know that all 6 time series appear under the weather measurement. Next, we have the set of fields. So we know that time series 1, 3, and 5 appear under the temp field, and series 2, 4, and 6 appear under the humidity field. And then lastly, we have the tag key value pairs. And each tag key value pairs will have 1 or more time series associated with it. So Denver has 1 and 2, Bellevue 3 and 4, and so on and so forth. So we use this when a query comes in, like the one we have at the bottom here. We're selecting the temperature from weather, where the time is for the last hour, and the state is New York, right? So based on the metadata and the information in that query, we can get to the set of underlying time series that will have to be scanned to answer it, right? So here's the query again, and we know, well, it's from the weather measurement, it's from the temperature field, and it's where the state is equal to New York. So we do an intersection of those, and we know that it's time series 5 that we have to look up, right? So what would happen if we changed this a bit and we actually removed the state qualifier. So now we're just looking at the temp field for all rows in the weather, right? All series in the weather. Well, in this case, we do the intersection and we see that we have to look up time series 1, 3, and 5 to answer this query. So looking at the underlying TSM data, it might look something like this, right? So we have a file with a bunch of these different time series blocks. And I actually left out the parts where, you have the start of one series and then the start of the next and whatever. There's also within TSM files an index as well so that you can read into it. So now that you have these time series blocks, essentially once you have the set, you consult the inverted index to find out which individual time series you have to look up. And then you have to go to all these different TSM files and look up the specific time series and look up the blocks that match. And again, the blocks are basically just time ascending order, right? So if we're looking for, just one value from each of a bunch of different time series, we're going to look up at all these different blocks, right? So we have in this example, 8 blocks, 8 different time series that we're hitting, right? So we end up decoding at least 8 different blocks of data located maybe in different files and definitely in different spots on the disk. Now, this design has a number of trade-offs, right? There are some things that is optimized for and other things that is not well optimized for. So the first thing is that it's very, very fast with low cardinality lookups and execution, right? So we have that inverted index. So a query that hits one individual time series or a dozen or so, or 100 even, it's really fast for that because it uses the inverted index to narrow down to those individual series, and then it can jump right to those spots to pull the data out, right? Now, the downside here is that you have to maintain that inverted index while you ingest the data. So as you're ingesting the data, as new tag values are being defined, as new measurements, new fields, whatever, as all this stuff is being defined, that inverted index has to be kept up to date. And you do this on ingest regardless of whether or not you're going to query the data, which can be problematic in cases where you have a massive ocean of data that you're ingesting and only a tiny slice that you end up querying. And then the other piece of this is the way the data is sorted. We sort the entire time series key space, and we have to keep updating that. So as you define new series, which by definition, anytime you have a new tag value, a new series is created, right? Anytime you have a new tag or a new field or a new measurement, a new series is created. So we have to maintain a sorted key space so we can assign IDs to these things and keep that all organized. And the point of those things is that this makes it expensive and slow for higher cardinality workloads, right? Workloads where you have a lot of unique tag values and a lot of like event workloads end up becoming quite a bit slow. And actually the size of your inverted ingest can end up being the thing that dominates, how much disk space you have to use to store and work with all this time series data. Now, what had happened in that period from 0.8 to essentially 1.8, it was a multi-year period, InfluxDB had evolved to become a time series database that stored time series, right? So like I said, originally we wanted metrics and events, and InfluxDB can still be used to store events, but really under the hood, what it looks like is it's a pure play time series database that has these individual time series and it has metadata that it maps onto those. So again, that comes with the advantages of that, which is really fast lookup for individual time series, but the disadvantages of slow to ingest high cardinality data and slow to execute analytical queries that touch many, many time series. Now, as I mentioned at the beginning of this talk, we're not really going to talk about the 2.0 cycle that much, but I did just want to bring it up a little bit. So with 2.0, we weren't really focused on the core of the database. We were focused on all the areas outside of the database, right? So we created Flux, which is the scripting and query language that makes it so that you can do expressive, powerful things in the platform. You can connect to third-party services and databases and combine that with your time series data on the fly. You can send alerts or notifications or webhooks out to third-party systems and do all sorts of complex processing and joining within the data. In the open source world, we created an all-in-one binary that contained the database, the user interface, and the processing agent to do background processing and monitoring and alerting. And then from a company perspective and a way we deliver software, we switched over to a cloud-first delivery model. So before that, we had essentially this monolithic database that we delivered as open source or an enterprise offering or a managed offering in cloud. We broke apart the monolith and we deployed it into all three cloud providers as a SaaS services-based solution that was usage-based on pricing. And our goal there was we wanted our individual development teams to be able to ship code to production on any business day. And we didn't want to have to ship the entirety of the database all in one go, right? This whole monolith. All right, let's come back to time series again. So this is one of the reasons I think the distinction between a pure time series database that actually stores time series versus a database that can yield time series on the fly from computation is important. It's this problem. With time series, you end up summarizing everything you want to express before you actually send that data into the database, right? StatsD was a perfect example of that. You could send a bunch of events to StatsD and it would aggregate them and summarize them and then write it into the database. And that's how I think about most time series databases, right? You decide ahead of time what dimensions matter to you and you summarize all this data and you feed it in. So to highlight this, I'm going to switch over to another popular time series database data model, Prometheus. So this was originally developed at SoundCloud starting in November of 2012, but it was an internal project. They didn't release it publicly until January of 2015. But its data model is basically the same as OpenTS2B's, and InfluxDB is similar, but a bit different, right? The thing that Prometheus did, though, is other than just the basic data model of metric, in their case, labels, which could be tags, value, and a timestamp, they layered on a logical data model on top, right? So you had this idea of time series that were either gauges, counters, histograms, or summaries. And in the case of histograms and summaries, they actually shoehorned that information into the labels. So let's work through an example really quick. So here is the Prometheus exposition format, right? It's the text protocol that you use to convey Prometheus metric information. And this could be going into a Prometheus server, or it could be going into any number of places. So say we want to track the request duration for a service we've implemented. As a Prometheus histogram, it might look like this, right? And this is if we only had 4 different buckets in the histogram, right? Everything that takes less than 100 milliseconds, everything under 500 milliseconds, everything less than 2 seconds, and then everything that takes longer than 2 seconds. And if we just have this really coarse-grained histogram, right, with no other information, when we write this data in, we're actually creating 6 separate time series, right? 1 for each of the buckets, 1 for sum, and 1 for count. And that's too coarse to be very useful. So you end up doing things like, okay, well, let's add the host that serviced the request. So we can see what the histograms and the performance looks like on a per host basis. So what we end up doing there is we end up adding 6 series per host that we have in. So the number of hosts in our infrastructure just multiplied the number of individual time series that we're tracking. Now say we also want to track the different service that's being implemented. So in this case, now we have service as a label, and now for each host that hosts multiple services, you potentially have many, many more time series, right? Again, 6 per host per service. What if we wanted to get a view of this service performance on a per customer basis, right? What if we put the customer ID in the label there? Well, then obviously you're going to be tracking 6 individual time series per customer, per host, per service, which gets really problematic over time, which is obviously why, the best guidance in terms of how to structure your Prometheus metrics is to not put high cardinality data into the labels. But then the problem you get back to is that you've summarized too much before it gets to the database. You can't get that per customer view. And the other thing is, as you add more dimensions to what you're tracking to your Prometheus data and in the pull model, you represent the full state on every scrape that you do, right? So if you add all these things in, you can quickly get to a Prometheus metrics endpoint that is hundreds of megabytes, or we've actually accidentally created one of a gigabyte before. Basically, as the number of metrics go up to give you more detail and more precision over how you want to look at data, the larger this problem gets. So one alternative to this would be you could use a push-based method where you actually just push a single event. Each time a request comes in, you push an event with whatever kind of additional information you want to use. And then the tricky part, if you push all of these underlying individual events, is how do you efficiently store them, collect them, store them, and how do you efficiently compute summaries or time series data from those raw events? Like, more importantly, how do you do that on the fly? So this problem is one that comes up, obviously, in observability quite a bit, which is this problem of like, what kind of precision or what kind of visibility do you need in these different systems that you're operating and monitoring? So the total other end of the spectrum from metrics, you have tracing, right? So tracing, both in distributed and potentially in in-process tracing, you can capture a level of detail so high that, again, the guidance is you have to sample your data. You can't capture everything, right? Because that's at the highest possible fidelity. So as an example, I executed a query in our production system against IOX that we have running there, right? So this is a Flux query that executes against IOX as the underlying core database. And a single query returned 119 spans. So what I tried to do here is like zoom out to kind of show the scope of this thing. And of course, what I captured here on the screen fails to capture even a tenth of what gets passed through. The amount of data and the amount of detail that gets sent is so verbose that it's just impossible to capture all of that in any economical way, right? And it's really hard to dig through. So it's almost like tracing, in my mind, tracing is for debugging. It's not for other kinds of things. So it's almost like within time series and within events and all of these kind of different data problems, you kind of have to match your precision to the use case that you're trying to serve, right? So when I think about event use cases, tracing could be one of those, but you'd have to sample. But there are other cases like, what if I want to capture a query log, right? In our case, we have a specific query that gets executed and we want to know the response time, right? And ideally, what we'd be able to do is do post-processing on that query log to kind of like bucket the queries into different types of queries, and then do comparisons between those different types, drill down to see how a specific customer's queries are performing, all that stuff. We don't need any of the tracing detail to capture that, but on the metrics side, it's completely useless to get that level of detail. So we need the raw event stream for the query log. Same thing if you're building an audit log of who accessed what and when. You need to capture the raw events, but at the same time, you'll probably want to create time series on the fly from this information so you can actually interpret the data. Usage metering is another one. So our Cloud 2 product is usage-based, amount of data written in, the number of queries executed, the amount of data at rest, and the amount of data going out. For that usage metering, we have to, log all of that information, and at the very least, we have to log it by customer. But then later, you probably want to log it by user or the API token that executed it. So you can do all sorts of, slicing and dicing to see, okay, where is my spend going? And really, I think a lot of analytics use cases, not just user analytics, but business analytics and system analytics, drive down to this kind of event use case. One of the things we've noticed, and obviously a thesis we've had for the last few years, is that columnar databases solve performance problems for storing events, right? They allow you to do these things at scale, and they allow you to execute queries very quickly on this data. Now, usually they've been used for complex analytics queries in data warehouses, But our thesis with IOX is that we can take that same technology and specialize it towards time series and for our use case. So let's go back to this idea of tables, right? So columnar databases represent their data as tables. In this case, what we're doing here is we're showing, okay, we have all these individual rows, right? That same data that I had before of the line protocol that mapped into these different time series and whatever. In this case, we're writing in these rows, right? So we have city, state, zip, temperature, humidity, and the time. Now, we're really not representing rows of data because ultimately you want to get down to a time series. So let's look at this query again. Let's get the average temperature from weather where the time is less than 100 and the state is New York City. You're going to execute this query, and basically it's going to execute on those bottom two rows and specifically on the temperature column. And really, actually, you don't need the zip code or the city to be pulled back to answer this query, which is where the columnar database part comes in. You can only look at the columns that are actually part of the query. So we can still work down to individual time series, but you end up having to process all the data in the table. So the nice thing is you don't have to do a ton of individual lookups if you're looking at a bunch of different time series. So how do columnar databases solve the performance problem, right, that we would have here, right? InfluxDB 0.8 had this table model, but we didn't have a way to solve the performance problem to deal with events. Remember that we said as tables got too big, the query execution got too slow. Well, columnar databases have a bunch of different techniques. This is only a collection of some of those things. But first, you have per column compression that helps you with the on disk space, right? So you have dictionary encoding, run length encoding, you have delta compression, all sorts of stuff. You have vectorized execution, basically so you organize the data in a way where the CPUs can get just churn through it very quickly through SIMD instructions. You can parallelize query execution. You can partition the data into different blocks. And then finally, once you partition the data, you can actually prune whole partitions from consideration for executing those queries. Right, so if you look at dictionary encoding and run length encoding, for example, like in city or state, basically depending on how you sort this data, you can get a lot of repeated values. So the dictionary will make sure that you're not storing just a bunch of strings, and the run length encoding will make sure that if you have a lot of repeated values, you can get efficient storage. So the other piece I mentioned was this idea of partitioning your data. So in IOX, we break data into partitions by default. In our case, we're breaking the data into single days, right? So we have measurement 1, we have November 1st as one day, November 2nd as another day. And when data comes in, we just write it into the correct partition. And what that means is when a query happens, if it filters by time, we can effectively eliminate all the partitions that don't fall into that time range and only execute on those partitions that are in there. So there are common things with this kind of a query setup. They're very, very different from the standard time series database of inverted index and raw time series. So the execution goes against all rows from the included partitions, right? So if you're going to access an individual series, you do it through a combination of pruning partitions and then brute force on the partitions that are left. The nice thing is, because of that vectorized execution, for an individual, for some types of queries, you can expect to get about 1 billion rows processed per second per core that you execute on, right? So that gives you kind of like a rough estimate for how quickly you can get through some amount of data. Now, we can further partition the data and organize it in such a way that queries can be fast to process on them, right? So in this case, say we have measurement 2, we partition by the day, and then below that, we partition by, region. So there's a tag in this data called region, and we split it up there. And the expectation there is that many of the queries will have a region qualifier in them, which will make it easy to rule out a ton of partitions. So remember these time series blocks from before? Well, in TSM, they were obviously blocks of time value pairs of 1,000 individual values. In IOX, these are called chunks, or well, there are partitions, and beneath that you have chunks. And a chunk is basically just a table, and it has a number of rows. And in our case, we'll actually organize those into millions of rows of data because the system can process, 10 million rows so quickly. And we organize that so that when a query comes in, we look at the query, we find out which of these chunks need to be hit, and we can go access those individual ones. And the nice thing is, because we're not accessing on all the individual time series, we can quickly process against 10,000, a million, 10 million, 100 million time series, and it's all the same. It's basically just rows of data that you're processing through. So this makes high cardinality queries that hit potentially, millions of series possible. It makes it much, much faster. Now, the trade-off here is that a query that hits an individual series may not be quite as fast, but it's fast enough so that you can render a dashboard in real time or build a monitoring and alerting system around it. So even within all of that, there's still some problems that we're looking to solve in our, columnar database IOX solution. So the first is this problem of wide tables, right? Tables that have many, many columns. And we've seen this in event use cases, and also definitely in the tracing use case where people want to have one table that potentially has thousands of columns. So we have some ways that we're thinking about to solve this problem. But it's definitely something that we're incorporating into the system. And then the last is this idea of sparse tables, right? So if you have a wide table that has, say, 2,000 columns, for every row you're writing in, you're probably not writing in all 2,000 values. You're probably just writing in 20 or maybe 100. So what you end up having is a table where a bunch of rows will have the same 100 values filled in, but a bunch of values are going to be null. And so again, you need to do some work to organize the columnar database so it doesn't completely die on that kind of data. Now, before I said partitioning, and the way you partition your data is kind of key to fast query execution, right? The best way to get fast query execution, other than to be able to churn through a bunch of raw data quickly, is to not have to churn through that data at all, right? So that depends on how you partition your data and the queries you have coming in. So ideally, the system would be able to repartition data over time so that it's optimized for the query workloads that are actually observed within the system. And then finally, you have secondary indexes, right? So this, for us, we want the base level user experience to be great. And we want to be able to solve most problems through schema design or partitioning. But we are holding out that for some use cases, we will need to have secondary indexes to answer certain questions quickly. And we want the system to have a design so that we can add those secondary indexes separate from the normal ingestion layer and all this other stuff that happens. And the nice thing is, IOX as the new core of the database is designed to be run in the cloud. It's designed to be in a containerized environment. It separates storage, which is object store, from compute, and that compute can be scaled up dynamically on the fly. And further, we break the compute workloads down into different types, right? There's the ingestion compute layer, there's compaction, which is totally separate, there's query workloads, and we can actually have different types of query workloads, right? Some set of query workers that process, say, queries that only look at the last few hours worth of data, whereas there are other sets of query workers that process larger scale analytical queries that are going to take longer. The nice thing is cloud databases solve for this kind of scale, and it makes it easier to modify the architecture as you go because you have these different pieces. The other piece we think about at Influx is this idea of federation, or really the idea of operating at the edge. One thing we see in our users and our customers that have IoT environments is they have high precision data at the edge where they want to process it with full fidelity. And then they want to have some sort of connection to a centralized system, right? Where they're maybe transmitting all of that data or just downsamples of it. So federation solves for that kind of scale and having many systems deployed globally, but we need distributed query execution around those federated systems to tie it all together. So InfluxDB IOX is basically the next evolution of the core of InfluxDB. As I mentioned, it's a columnar database. It supports SQL natively as a query language, specifically the Postgres dialect of SQL. I said it's a cloud database, which means, we have this idea of different services. We separate compute from storage. We use object store, and it's federated at the edge. And I'm happy to announce that it's actually available in InfluxDB Cloud today. So we're running an invite-only beta of IOX as the core storage system, but it's basically our entire Cloud 2 setup. So you get all the features of cloud, but using IOX with infinite cardinality and tiered data storage. InfluxDB IOX is what I call a time series database for storing raw time series data, but it's also a time series database for calculating time series on the fly from raw event data so that you can have data at any level of precision you want. Thank you.